Hello there, Math 125 fans. Going to continue our integration exam 2 review. Partial fractions is a big, important topic with lots of key connections to many areas of mathematics. So it's one you need to know. You're going to immediately see it again when you take Math 207. At the end of Math 207, the last 2 weeks, you do Laplace transforms. The entire technique involves turning something into a partial fraction problem. So you have to embrace it. As a student, I really liked partial fractions because I was like, okay, it just turns it into an algebra problem. And once we solve the algebra problem, we're done. So it's something you've never really needed to do before when you encounter it, because you're having to break up fractions. And when in your life did you break up fractions? You had to learn to add fractions in grade school, but never did you have to pull them apart. Okay, so there's also a ton of theory. So there's always natural questions students ask, because we're overlapping with these huge areas of mathematics. Okay, so let me shrink my gigantic head here. And let's go. So this section is about rational functions, meaning you have a numerator and denominator. If you don't know the difference between a numerator and denominator, there's a fine line between them. I've never gotten anyone to laugh at that joke. Okay, so anyways, the point is that we have to reduce. I'll do an example of that in a second. I'll do 3 examples. We have something called distinct linear terms. These are all to the first power. This is a distinct linear term right here. This is a distinct linear term. Distinct linear term, distinct linear term, distinct linear term. There's a huge topic in mathematics, which is sometimes you can factor. You know, if you have something like x squared, so just a brief, I don't want to spend too much time here because we have too many things to do. But, you know, when you're solving, sometimes you can factor over the reals, we say. And that happens in a lot of cases. But you know that there's some cases where you can't factor, and those are called irreducible quadratics. It turns out if you go to a higher power, like a 20, it also factors into distinct linear and irreducible quadratic terms. It's part of this thing called the fundamental theorem of algebra, which says everything can be factored over the complex numbers, and anything that can be factored over the complex numbers comes in pairs, and so you can get to irreducible quadratics. So there's a whole bunch. You need to go take abstract algebra to study all that. That's beside the point. The point is, this is everything. We don't need to go further. The only case that we skip in this course is what if we have irreducible quadratics squared or cubed. But, you know, those just get to be really long, and it's the same idea. All right, so if it's distinct linear terms, you write this. Why do we write this? Because it's possible. We talk about why it's possible. Is it the only decomposition? No, but we would like to get a decomposition that we know is possible and that leads to integrals we can do. And we can do all those integrals quickly. What about if it's a repeated linear term? Then we do this. We're really trying to write the most general form we can. I've explained this in a number of different ways in class, but that's not really for this video. For these ones, we know how to integrate those. Okay, so we're reducing to things. The integration step will pretty much be one step. And then we have the one case, the irreducible quadratic, where there's a square here. If there's a plus, it's not reducible over the reals. Okay, so what do? We write it in this form. And then my advice to students, which is different than what some people say, is when it is time to integrate that, we split it into 2 problems. We write it as bx over x squared plus 9. I think this is the fastest way. C over x squared plus 9. So ultimately I like to split that in 2, and then I go, this one we can do as substitution, and it leads to this. This one we can do with arctangent. And the point of that is we have taken care of everything. All right, so that's the idea of this section. There is this bit of algebra, which is how in the world do you find those numbers A, B, and C, and I'll do a couple of examples. All right, so that's as fast as I can do it. If you want, always you can go to my materials page. You can see my lecture notes, but that's the plan. So to me, that's really self-contained. I mean, I just explained everything in a few minutes. So as a student, I liked this section. I know that students tell me otherwise, but I'm hoping you can embrace this. And it doesn't matter whether you want to or not. If you're going to stick around in math, this is really important. So step 1 is this reduced. Well, the power on top is 1. The power on bottom is 3. We call it the degree, the largest power. So the answer to is it reduced is yes. Okay, next step is we factor the denominator. So we're going to do x minus 8. As I said, I like these examples where, I really don't have to think. This is very formulaic. I have a repeated linear term. I have a distinct linear term. And so what do we do? And I'll say something here. I'll give my little explanation, but we write this down up to when it repeats is what you learned in the section. Or if you didn't learn it in the section, you're learning it right now. A few students say, well, why do we do this? If you think about the most general term, it's in order to make things match up. But if you think about the most general term you could have here, you could have x to the first power on top and it would be reduced. So if we were trying to write the most general form, we would write ax plus b. That's the most general reduced fraction. But you might notice that that is exactly what this is. We just usually like to separate it out. And it continues if it was x cubed. Ultimately, you have to have, in order to get two polynomials to match up, you have to have enough coefficients. And the number of coefficients has to match this number. So if you don't have 3 things here, something went wrong. It won't be possible. That's kind of a linear algebra topic. Okay, so then we cleared the denominators, and there's a ton of shortcuts, but I tell students in Math 125, it's probably dangerous to learn too many shortcuts. Let's just learn the ideas first, and then save the shortcuts for Math 207. Because I've just taught this course too long and seen too many students do shortcuts incorrectly. Okay, so we're trying to find numbers a, b, and c that make these two sides equal for all values, and there's 2 techniques. And it's good to know both. One is the special value technique. And there's a bunch of stuff we can say about that. Again, this is hitting on a huge area of theory. But if these 2 things, if it's possible for these 2 things to always be the same, then they should be the same for all values. And so we're going to plug in special values that are easy to check. Now, there's one a professor years ago that would say he really objected to what I'm about to do, but it's fairly standard. The complaint is if we plug in 0 here, the original function was undefined at 0, so we're actually doing a continuation. So there's a mathematical complaint about this approach. But we're just going to plug in 0 everywhere because it's going to make a times 0, and it's going to make b times 4, and c times 0. So it's going to be a times 0 plus b times 4. And once you do a few of these, you don't write all that stuff down. You just solve for b, and you say b has to be -2, and you might even be able to see it right from the get-go. Okay, so we have learned one value by doing this little special value trick. Is there another special value we can plug in? Sure. How about -4? We plug in -4, we get a -12 on the left, we get a times 0, we get b times 0, and we get c times -4 squared, so c times 16. So c is -16 over 12. Let me double check my screen to make sure I'm not going off the screen. Okay, that's right where it is. Oh no, why did I do that? Click the wrong thing. Okay, so here we go. That, well, divide top and bottom by 4. It's -3 over 4. Yay, and I was going to check. I don't like checking my notes. I never do it in class. I want students to yell at me if there's something wrong, but there's no chance for you to yell at me right now. So I will check my notes to make sure because when I have an error in these videos, people hound me for it for years. Sometimes I get an email from someone in Europe saying, I found an error in your review sheet. What's wrong with you? I'm like, oh, I was trying to help. Okay, so next, what do? Some people tell students to plug in special values. I don't do that. I go to the source, meaning I want to make the 2 sides equal. You can do this very fast, but for the first time since I'm explaining and you weren't in my class, I will expand this out. This is not fast to do it this way, but I'm expanding this. And then I have plus bx plus 4b plus cx squared. Okay, just checking something. Great. We want the two sides to be equal, and this really illustrates the point. This side is a quadratic. It has an x squared, it has an x, and it has a constant term on the right. You might think about what those are. On the left side, it doesn't look like a quadratic, it looks like a line. An important principle of polynomials is two polynomials are equal only if all their coefficients are equal. And that's actually a governing principle in all of this. And that's why you need three things. That's part of the reason I'm saying this. But here I have a plus c. A plus c. And stick with me here. What does a plus c have to be? Well, how many x squareds on the other side? There are none. Now, did I need to expand that out to see that? No. I could have seen it back here. A plus c has to be 0. That's what I would have done next. A plus c is 0, so a is negative c, which is 3/4. You can use this, though, as a check. Now let's look at the coefficients. Let's look at the constant. The only constant here is 4b. 4b has to be negative 8. But that means b is negative 2. Hooray! So it's nice to have a double check. What about this constant? We have 4a plus b. 4a plus b has to be 1. That's a coefficient there. Is 4 times a, so 4 times a would be 3, plus b, which is negative 2, equal to 1. Yes, hooray. That's what's going on. So that justifies what we were doing with this form back here. There were three things, so now they match up. Okay, I spent too much time, but since not all of you had me as an instructor, I want to make sure we had that because there are so many questions students ask. Anyways, so then when we're done, we just have to remember what A, B, and C were. So A is 3/4. And apologies, somebody posted about me saying that I have the worst penmanship. I'm sorry. I'm trying to help. Okay, x squared plus negative 3/4 over x plus 4 dx. The price is right, though. You're paying $0 for this. And I'm getting $0. Why am I doing this? Okay, so here we go. Let's integrate. This is 3/4 log of x. That's one of the ones we know. This is not the log. It's the x squared. So it's negative 2x to the negative 2. So power goes up, becomes negative 1, divides. This is going to become plus 2x to the negative 1. Negative 3/4. The log of x plus 4 plus c, success. If you want to know why the absolute values are there, I always have students asking about that. I have a video about that. I have a lot of stuff, you know. Any question you have, I've probably tried to answer at some point for some student. All right, hope you find that helpful. Let's hit another one. All right, so here we go. And I just want to hit an example of kind of each thing. So I don't know why that's not working. Constantly fighting me. Darn computer. Okay, what about this one? This one illustrates a key point. The power here is 4. The power here is 2. It's bigger. I need to divide. I like doing polynomial division. I guess because there's something wrong with me. But because I remember in grade school having to do long division, like big numbers, 26 into 500, you know, whatever you had to do. And I remember that being somewhat painful because you had to think about how many times it goes in to this. Okay, one time, and then you had to subtract. Okay. I found that harder than this. I think this is much easier. How many times does t squared go into t to the 4th? It's t squared. I know there are other ways to do this, but we can just rely on a process we already know. You say, well, I don't know how to do long division. Well, how'd you get here? Okay, so negative 9x squared plus x. We can get you. Even then, I always think we're not going to blame your past. We can get you through all this. Negative 9x squared minus 81. You say, what is he doing? I'm doing the same thing I do when I do long division. Okay, let's subtract. You don't have to make sound effects, but it kind of makes it more fun. When do you stop? Well, when the power gets smaller. And what's the conclusion? The conclusion is it went in this many times, and this was what was left over. All right. Let me make sure I didn't write something ridiculous. Actually, I don't have this one at the ready, so we're just going to wing it. We're going to go without a safety line, which means I've probably made a mistake somewhere. Okay, so there we go. I don't want to try to locate this. Now that I thought I had it open. Spring 20, oh, I do somewhere. I just don't have it on the right problem. All right, let's check. Let's get our safety wire. Nope, I don't have it. Great, good. I don't want to look it up. So after you do that, and you've completed your long division, now you're going to ask the question. Let's grab this in case we've forgotten. Which form are we in? Well, two of these things I know how to do already. 1/3 x cubed. And if I did something wrong, you can tell me in the comments. I'm not going to remake the video. I'm focusing on ideas. We have one of these. I mentioned how I like to integrate something like this. So it's already reduced as far as it can go. So there's no partial fractions needing to be done. But if you were listening earlier, which is weird for me to say because I think that anyone that's still watching, I don't believe anyone's still watching this. Give me a like or a comment if you're still watching at this point. I think it's valuable what I'm doing. Somebody will watch it someday. All right, here we go. So then let's integrate. This one, I allow students to do this in one step, but it's substitution. If you call this u, then du will be 2x dx, so you get this 1/2. So you get 1/2 the log of x squared plus 9. Technically, you don't need absolute values because it's positive. You can do an immediate check, which is what I like to do in my head. I take the derivative, x squared plus 9 times 2x, success. Now, I'm doing that quickly. In class, I would spend more time. This is then an arctangent, 82 over... This is the one I actually have. I pause in my head because sometimes I can't remember. Is it a 9? Is it a 3? It's a square root. So it's going to be 3 arctangent of x over 3. And I could derive that too. It's substitution, success. Let's keep going. What about this one? What do we got? We have a repeated linear term and a distinct linear term. Off to the races. X squared over x minus 1 squared. X plus 2, we get a over x minus 1 plus b over x minus 1 squared plus c over x plus 2. We cleared the denominators. 9x squared equals ax minus 1. Uh-oh. I often have to talk with students in office hours about this, about physically putting this. So if you need an extra step, I mean, if I've met a lot of students that even after the final, they still don't understand how to clear the denominators. And it looks like I don't either because I was about to make a mistake. But you can see how I'm illustrating how I check as I go. There's a lot of double checks in everything I do, and that's what you really want to be practicing as you're doing the homework, is your ability to look back and forth and not blindly move forward. You're not stuck with making silly errors because you can check as you go. All right. So anyways, I'm going to plug in special values. Let's use that method. If we plug in a 1 everywhere, we get 9 is equal to, this is a 0, that's a 0, b times 3, because we're plugging in a 1 everywhere. So now I know that b is 1/3. No, it's not. You can see that I'm checking. I don't mean to be illustrating this, but you can see I have had to learn over the years how to check my work. I'm not because I'm good at arithmetic. It's because I've practiced. Okay, so I'm going to put a -2 here, and a -2 here, and a -2 here, and a -2 here. So it's going to be 9 times 4 equals 0 plus 0 plus -2, so -3 squared, 9c. And if you can trust yourself to do a little arithmetic like that, that's going to be great. But I know I'm going to check my work in a second. Divide both sides by 9, I got c. Okay, you got to love this erasing I'm doing. Now I'm going to compare coefficients. Let's see if we can do a little better than last time. I can see right away. Take a second and see if you can see what I see. If I were to expand this out, I'm going to have an x squared, I'm going to have an x, and I'm going to have a constant. Can you see the x squared? I know what the x squared is on the other side. It's 9. So I would like to say 9 equals whatever is in front of x squared. And once you get this idea, you go, oh, this is fast. There's going to be an x squared from there, and there's going to be an x squared from there. Those are the only ones. So there's going to be an a plus cx squared. You say, but you didn't expand everything out. No, I didn't, because I didn't need to. I'm just looking for a. So once you get this combination of ideas, oh man, this goes fast. A minus c, so this is 5. Boom, baby. So then we integrate, we're going to get 5 over x minus 1. We're going to get 3 over x minus 1 squared. We're going to get 4 over x plus 2. We're going to get 5. I'm probably off the screen. Let me double check my notes here. Almost. Log of x minus. So I've got a new computer, new setup, which is good, but I'm kind of figuring out the best layout for me as I work along. Ah, that was pleasant. Let me take a look and see. Hey, it matches my answer. All right. I think I hope I illustrated to you that that's a topic you can hammer out and do well on. All right. I didn't hit everything, but I hit most of the things. Let's stop there.